Hello everyone, welcome to this session of cloud computing and security. So in the first module here we have five chapters which we have to study, and as you can see, the first chapter has three subtopics. The second has five, which is most lengthiest. If you see here, 5 to 13, 13 to 27, 27 to 36, 36 to 40, all are less than 10 except for this second one. So we'll start with the scalable computing over the internet. The thing is, under the age of the internet, we again have a few subtopics which I have already written down and kept in my paper, like my own notes. But you don't have to worry about that. Under the first topic, we have six. Okay, so just a second. 1.1, 1.2, 1.3. So yeah, so this one topic. Wow, if I attach it to see this age of internet has six subtopics again. The scalable computing has four, and the IoT is just two. The easiest part is the Internet of Things and cybersecurity. Scalable computing trends and new patterns like something like new and advanced technology which have to remember. The age of the internet is like from the beginning till present. So we'll start with the chapter. So here is the key points of the first chapter. I mean 1.1, what we will be studying, like how the rise of the internet event, a shift from high performance computing to high throughput, evolution of computing pattern, like how we introduce clusters, grids, peer-to-peer, clouds, and IoTs. Importance is scalability, efficiency, and service orientation is a main outcome for this new technology. Then we have introduced to three major new paradigms, that is SOA, server over application, something like that, Web 2.2, and IoT. This is all about search engines and all stuff. That AI, IoT is about sensing and monitoring the data. This is all about communication. We'll see that just now. And comparison of computing models. We have four centralized, like all connected to one single system, parallel, like more than one thing are running together at the same time. Distributed, multiple computers are connected together via any online material type of thing. Cloud it's like it's all virtually distributed. Is like systems are interconnected. Clouds are like all completely virtual type of thing. Goals of modern distributed system: efficiency, dependability, and adaptation flexibility. Okay, so now evolution of computing platforms is like the age of that thing. Over the decades, computing has evolved. See, from mainframes to microcomputers, from microcomputers to PCs, and now to distributed systems. Like, what are the distributed systems? See, these distributions are nothing but clusters, grids, clouds, and IoT. So you can start from mainframe to computers, microcomputers, sorry, mini computers, then from that to PC, personal computers, and then from that now distributed systems, which are these four things. Internet-based computing are focuses on large-scale data-driven applications requiring parallel and distributed systems. You saw here, right? Parallel and distributed systems. These both are nothing but comes under cloud itself. This is the old way. I don't recommend this centralized computing. Not good for most of the things because it has a major downfall. Like everything is connected to one system. If that one system fails, then everything is gone. It's like that. HPC versus HTC. Though this is just two lines, but you can see, since I have highlighted 4 points, then you can not 4 points, it's 3 points. So you can actually elaborate this and write it for multiple things. But once first let us read this, then we'll also compare it with textbook and see age of the what to say internet computing, the platform evolution. That's what HTC and HPC comes. So here, high performance computing focuses on raw speed only, like the actual speed on how it will process. But high throughput is like it focuses on completing many tasks efficiently. In the sense throughput itself, like how much time does it take to complete a set of tasks in a set amount of time. For example, within a minute, how much data it has processed, or how many packets have been processed, like that. So it focuses on high throughput in the sense in 1 minute it wants to travel 1 million packets, like that. But a high HPC is like how fast can I process. Like it doesn't require, like it doesn't have a goal. It's like I just have to be fast, fast, fast. Like the maximum limit, the max rate at which high speed you can run. It's like that. Then high HPC is used in science and engineering applications, and how HPC is measured, like using benchmarks and like link pack. So basically, you see your phones and stuff, right? What to say? How do you give the spec ratio and stuff? It's all benchmarks, right? Like they're measured using benchmarks. While coming to HTC, they are commonly used in like, the most common application which you use in daily life, web service and search engines like Google, Safari, all those things. They emphasize throughput, cost effectiveness, and energy efficiency. From the name itself, we can understand throughput. So they emphasizes throughput, cost effectiveness reduces the cost compared to other platforms, and then energy efficiency. Usually energy efficiency, whatever search engines we use, they have their own hardware components in their headquarters or actual place, like ChatGPT. We heard that many GPUs got melted down because of those ghibli images or stuff. So basically those things produce that carbon components and all, which affects the earth and environment. That's why they say about green efficient energy efficiency or green energy stuffs, so that the AI which you are using, the hardware, the GPUs which are producing the text and prompts, they shouldn't produce any harmful energy. It should be green, like that. The diagram over here you can see the HPC have, it's either in the form of clusters. The HPC systems are in the form of clusters, but whereas the HCC are in throughput forms. So there are usually many MPPs present. These MPPs are converted to cluster forms. If you check in the textbook, you will be able to understand. Mm, See over here, massively parallel processors are gradually replaced by clusters of cooperative computers out of desire to share computing resources. So, in the diagram which you could see, these MPEPs are converted to clusters for sharing computer resources. These clusters are often a collection of homogeneous, homogeneous compute nodes that are physically connected to the close range to another. Then in HCC, we have peer-to-peer networks are formed. A P2P system is built over many client machines. Okay, a concept we will discuss. Okay, that's not for us. Peer machines are globally distributed in nature. P2P. That's it. We don't have to see much. If you have to see the diagram, you have see P2P is for HTC, and clusters and MPPs. What are MPPs? It's the full massively parallel processor. Then these both form are given, see, disparate clusters and geographically sparse, computational and data grids. What are those data grids? Three are there: web 2.0, internet clouds, and internet of things. Okay, if you remember this internet clouds as that SOA, see, service oriented architecture. This thing you can imagine. So major paradigm shifts. So if you see here, high performance computing, high throughput computing, that's the same basic thing. And the textbook we have this topic, the three new computing patterns. Those are nothing but the major paradigms. Say it's a paradigm, it's not paradigm, it's paradigm. First one is SOA. It focuses on modular service design. mm, you can see here SOA over here. What they use also is there. We will study in detail SOA. So see, since they have told that SOA will be studied in detail in chapter 5, which is probably in module 3 or 4. So you don't have to write much about it. So obviously they won't ask much about this. Even though if they ask, then when you study module 5, you can automatically write the content over here. Just for now, you have to understand that focus on modular service design. Web 2.0, it's enabled interact web application. You can talk about search engines, all the Google things which you do. See, you do, right? We spoke about them here. Search engines and web services, all those things. Then IoT is like integration of sensors. This is RFID. What is RFID? We just read over here. That is radio frequency identification. GPS is global positioning system. IoT, Internet of Things. Minimum, no, that's it. So here internet is basically what you are interacting with physical objects. Okay, not with physical world. Interacting with physical world is something else, which we'll see at the end of this 1.1 session. So remember, IoT is like using this sensors, radio frequency identification, GPS. We interact with real-time physical objects. Then notable codes in the Internet of Computing, you can use this to enhance the quality of your answer. The network is a computer and the cloud is a computer. These two statements were given by two different people, the codes. One was at John Gage and the other was Rajkumar Bhuya, something like that. So remember, John Gage told about network and Rajkumar told about cloud. So this guy said network is a computer and Rajkumar told cloud is, cloud is a computer. Yeah. Then you have computing paradigm, which are four we saw in the beginning of the model, like central, parallel, distributed, and cloud. So if you see here, you have computing paradigm distinction. So you have four things: centralized, parallel, distributed, and cloud. Okay, so these four itself are broken down into very simple things. This description, if you understand this one line, then you can write additional points for that. All resources located in one system, they are tightly coupled. So all resources located. So see, tightly coupled. Parallel, multiple processes working simultaneously, shared or distributed memory. So more than one processor is running. You can say like parallel paradigm. You just from the parallel, see at a time, more than one are working like running together. Processors, multiple processors are working simultaneously. It can be like each processor is working on something else, like two different things, or you can say they are working on the same thing, like same thread or same task, like that. Distributed interdependent computers connected via network. See, communication via message and passing, like your Canva. If you have in Canva, you can share your project, so multiple people can, you know, interact at the same time, or you're in a video call, or it's like that, like connected via network. Cloud, what is that? Computing, cloud computing paradigm, internet based computing combining features of centralized and distributed models. So you can simply tell it's a combination of these two. Then you have about ubiquitous and internet communication. Ubiquitous, the term ubiquitous in the sense it's available everywhere, like no matter where you go, it's available everywhere. For example, of humans are everywhere. No matter where you go, you can find humans except for jungles. So for that, you can say animals are everywhere. Even humans are animals, like just human beings. They come under animal species itself. If you have studied biology, you would know that. So if you say animals are everywhere, so it's kind of like that. You cannot say trees are everywhere because you cannot find them in deserts and stuff. It's just like that. Ubiquitous is like computer, like smartphones. They are everywhere. No matter where you go, you can find a smartphone in like actually in every block of the city or every home itself. So ubiquitous computing allows interaction with computing systems. So anyway, so that's all. So interaction with computing systems, you have to remember that from everywhere. That's it. IoT and extension that connects physical objects to the internet. I told that IoT, Internet of Things, via sensors, GPS, RI, what is radio frequency identification, RFID. All those things they help to connect physical objects to the internet. Then internet computing covers all paradigm using the web as the medium. Then distributed system families, once you complete this, you have this distributed system families which have efficiency, dependability, adaptation, and flexibility. So first we have this, and then goals of the families are this. So what are the distributed system families? There peer-to-peer networks, clusters, and grids and clubs. What is P2P network? They are decentralized. Remember, even in future topics, you have to mention what is where they are decentralized. They follow peer, structure used for content sharing. Then you have clusters and grid uses multiple interconnected systems for computation. Multiple interconnected systems, they can be connected via network or internet. You can rewrite an additional point. Clouds uses virtualization of scalable and on-demand services. So suppose you need any services like basic services of your daily life cycle, which like you have this. What is that from you have urban service something, which a good example for that cloud thing. So here it's just an example for on demand things. Here since it is cloud, so like virtual assistants of you have in all of your like Flipkart, Amazon, they have this new AI, right? Talk to this AI and all. Most of the platforms are releasing their own AI, so it's also about that itself. Goal: efficiency, utilize computing power and energy effectively. Efficiency about computational power, how well you're utilizing the CPU, and the energy, how well you're managing the energy. Dependability, how you can depend on the system, like how reliable it is, how much time will it run without giving any errors or stuff like that. Ensure reliability and fault tolerance. Adaptation handles diverse workloads and changing service demands, like uh, based on previous year thing and now like latest techniques, technology, services, how well it is able to adapt to those things. Flexibility supports scientific HPC, and so it's like supporting both HPC and HTC. HPC is for most scientific, HTC is for business. That completes this part. We'll move to scalable computing trends, the new paradigm. So here we have completed 1.1. 1.1.1, we have to move to 1.1.2. Like we said, we have three things, so in that one is completed. This don't worry, it's not much. We'll directly move to technological trends driving computing. It's like Moore's law and Gleider's law. It's very simple. What Moore's law says, processor performance doubles every 18 months, and Gleider's law says network bandwidth doubles every year. It's just two things. Then we'll move to the degree of parallelism. We have many things mentioned over here in this degree of capacity. You have here PPL, ILP, WLIP, and this SMID. We'll see that over here. So see here, BLP is nothing but bit level from serial to word. It's just converting like that. Instruction level parallelism, it's like pipelining type of things. Execute multiple instructions per cycle. Data level, same operation on multiple data. Okay, it's like SMID, single instruction, multiple data. Okay, vector machines execute same operation. Like for example, you have to upload some file. You are uploading a file same, but on multiple places, in multiple websites and stuff like that. Task level, like going live in multiple platforms at a time. Task level parallelism, concurrent execution, thread process, like at the same time. Parallel, say like pipelining, there you are executing instructions, here threads or processes. It's like that. Job level, coarse grain parallelism is suited for coarse grain, and you have fine grain. Fine grain, you will see that at the end of the chapter, it's here itself. So here, innovative application of HPC and HTC. Science are more like climating or weather type of thing. Business like marketing, money and all. Web, search engines, government, public services, traffic control tracks and all. Military, it's a crisis management intelligent command system. Like suddenly, you have to evacuate the whole city. You have seen movies, right? It's like that. Then you have application require transparency and accuracy. Okay, this is the main goal. Utility computing and emerging paradigm. Utility computing is like electricity. You pay only for the service you took for, like mobile data and stuff, or that Wi-Fi. Cloud computing is broader version on-demand services of the internet. They support. See, I told you right in the beginning of the chapter. You have to remember the scalability, virtualization, distributed application. Features of Bono paradigm: ubiquitous, accessible from everywhere, autonomic, self-managing and dynamic, composable, SLA and QoS driven services. See here, paradigm grid, cloud, P2P and web. Grid is federated resource sharing, cloud computing, on-demand, virtual service, P2P, decentralized and peer level. Web services, computing, interconnected service and APIs. Hype cycle, they have spoken about this. If you check in the textbook as well, in the hype cycle, you just have these four things. I'll tell the 5 points over here. Technology trigger, peak of inflated expectation, through of illusionment, slope of enlightenment, plateau of productivity. How you have to write this? See, the cycle shows the expression for the technology in 5 stages. First, it rises sharply from the triggered period to a high peak of inflated period. Then triggered is the initial period, and high peak is like the highest matured time. Through a short period of disillusionment, the expression may valley drop a valley means a lot, and then increase steadily over a long enlightenment period. In the sense, like suddenly it goes down. Like obviously you have that peak, right? It goes full up, and then that one comes down, and then it gradually keeps on going up to a plateau of productivity. That's it. Then you have 5 symbols through which you explain. See, hollow circles like reaches maturity less than 2 years. Solid circles takes 5 to 10 years, and then triangle takes less than 10 years. Sorry, I said less than. It's like takes more than 10 years. You can see this one word 5 to 10. Okay, that thing itself is wrong. Cross likely to become obsolete in the sense, like it won't what to say, permanently. It has like lost that thing, like empty box type. So it won't have any increasing like that. It's like rejected type. Like it won't be used much anymore. It's like that. Like put a full stop for its career like that. That's it. Then you have hype cycle status, using a technology example. Cloud computing just passed the peak, and it took just 2 to 5 years for it to mature. Internet micropayments like Bitcoin, Jeep and all in enlightenment phase. 3D printing took 5 to 10 years of maturity. You can give that solid black dot over here. If I do like this, I'll just put, so it's just a solid dot. Then mesh network, it's that triangle thing, right? This should have that triangle thing over 10 years, and this is a hollow circle. We don't have any shape for this inline interface except to become see broadband over power line. So you have to put cross for this, just like that. Then conclusion that completes it. 1.2. This is the shortest part: the Internet of Things and cyber physical system. Key topics covered: IoT, basis of CPS, communication pattern of IoT, technology enabled, future implementation, etc. So IoT is what refers to a network interconnection of everyday physical objects via the internet, enabling them to send and receive data. Origin introduced in 1999, that is 1999 at MIT. Concept evolved from traditional internet, which focused only on machine to machine or web to web communication. What is the pattern of IoT? Human to human, like how we both are doing. Human to thing, like how the AI uses my content to train some model. Thing to thing, like how thing to thing is like we don't take AI and all in here, like sensors to actuators, that are things to thing. Okay, human to thing is like feedback type of thing, how you gain something from data, like monitor or something. Human to thing communicate like that. Technology used in IoT: radio frequency identification sensors for collecting the data via connecting to actuators in physical objects. GPS, global positioning system from satellite and stuff. IPv6, which we studied, it's like, remember, like you have IPv4 and IPv6 like that, provides to the power of 128 IP address for unique identification of assets. I just say IP address for unique identification of objects, or else object identification. Scale of IoT. Future estimation, they say that 100 trillion objects may need to be tracked, like like 100 trillions, a lot of number, very big number. Each person may interact with 1000 to 5000 IoT devices. In the sense, in your daily life, like it will become like obvious that you will interact with 1000 to 5000 IoT devices, which you might not be knowing for yourself that I'm interacting with so many devices, but will actually be interacting with a lot of devices. Challenges, it's basic. Instead of thinking it as challenges, you can simply tell that what it's doing, the services, what it is doing, providing services, identification and searching. You can talk about GPS over here. See, addressing, searching, identification. It's a complexity in that. Then smart home services, smart lock and all, security and privacy concerns, and need for low cost and intelligent communication. It should be cheap and efficient. Goal: creates a smart world with smart city, clean energy, efficient healthcare, intelligent transportation, etc. You can write multiple things based on your own knowledge. While coming to CPS, it's quite similar to IoT, but the only difference is in it is a system in which computational elements, here are the only computational elements, control and interact with physical entities in a closed feedback loop. You can say physical world. So two main components, which is cyber, one is physical. What is cyber? Heterogeneous and asynchronous computing systems. Physical in the sense real world entities with concurrent data and data rich behavior. It can be anything. Okay, physical world, real world entities, it includes animals, living and non-living objects as well. Core technology, there are three C's. Simply remember the three C's: communication, control, and computation. Your order is your own, which you can rearrange in any order. So it's like one is about computer, how you communicate, and then control. Computation, communication, computation. You can write about your own, how the processor, how it computes the data and all stuff and all. Communication, sharing of resources. Control, how it controls these resources. Difference between IoT and CPS. IoT, interconnection of physical objects is object, and here real-time interaction with physical world. Application, IoT is like monitoring, sensing, and data collection. Like how you remember a sensor in your mind and do it like that. Here CPS, it's a closed loop control via virtual reality and automation. Research origin, it's mainly in Asia and Europe. Here it's United States. You have a quiz question. You can pause and check if you want. I'll soon be uploading this same PDF in the playlist description once the what to say this is finished. What to say whole module finished, so that you will be having this all these markers and everything. So you can see which of the following is not a typical communication pattern ID. You can either pause because I'm going to say the answer. This is the server to database. You don't have this. Which technology enables enabling a unit ID, that is a unique ID to each object in the IoT? Is it Bluetooth? See, we had this, right? We didn't have VPI and this and all. RFID. Oh, already the answer is given. Oh, I didn't see that. The core components of cyber physical systems are client server, no computation. See the three C's. Okay, which of the following is true about CPS? I'll hide the answer. It only monitors data. It is limited to. It is true, right? It performs real-time control over physical system. The array. Okay, whatever. We knew what the answer was. Then which of the following offers the largest IP address? One to the I to the 2 to the power of 1 2. That's IPv6. A short answer define IoT things. See all those things with the answer. Then we have to move to the 1.2.1, which we will do in the next video.